Uh, Good morning, everybody. I'm Granthana Rangaswamy, and today with my colleague Arushi, we would like to talk to you about parametric analysis. Now, firstly, a big shout out to our parametric analysis team, Matt, Herman, Selena, Yuvan, and Abhishek, without which we would not be able to implement the parametric analysis that we're going to talk about. Now, what exactly is parametric analysis and why do we even need it, right? Here we have a simple system that we're showing with like 8 compute trays and 4 switch trays. Now, as you can see with this simple system, there would be thousands of interconnects just to implement the any-to-any connection that we would need to have, right? So we would have thousands of interconnects here. Now, traditionally, as we all know, in the networking data centers, the data rates have doubled in every generation. We have gone from 25 gigabits per second at NRZ to 56 gigabits per second in PAM4, and to the current 112 gig to 24 gigabits per second. Now, when you change the channel encoding from NRZ to PAM4, the signal-to-noise ratio reduces further. We went from NRZ to PAM4, the SNR reduces by 9.4 dB. So what this really translates to at the physical layer, at the channel layer, is that the signal-to-noise ratio is reducing, and as a result, your margins are reducing. Now, if we take this particular system and then expand it to the AI clusters that we are talking about with thousands of systems, what that means is we would have millions of SerDes, millions of interconnects running at extremely high speeds, low margins, and we would have to have a system that is extremely reliable too, right? The UU metric, the unplanned unavailability of resources, has to be extremely low. We have to have minimal job restarts. The interruption rate has to be extremely low. So as a result, we are building faster systems, bigger systems, and an extremely reliable system. So that is the goal. So this is where parametric analysis comes into picture, wherein we want to get ahead of the problem. We want to proactively detect any kind of issues that can arise due to an interconnect. That could be from the SerDes at the transmitter, the channel, and the SerDes at the receiver. So this is where we would like to build a framework with parametric analysis, wherein we want to have richer telemetry. We want to collect data at scale, analyze the data at scale, so that we have valuable insights into how a system is really behaving. The system is not a black box anymore. We know exactly what the SerDes parameters are for each particular channel at the system level, slot level, port, and even at the lane level. So that is the kind of framework that we're talking about with parametric analysis. Now, I alluded to richer telemetry, right? Now, what do we mean by richer telemetry? Now, here's a generic block diagram of SerDes, wherein you have the transmitter with your 6 or 7 tap equalization, your feed-forward equalization taps, right? And then you have the channel, which is the millions of interconnects that I was talking about. And now with the channel is a low-pass filter. A channel is a low-pass filter, a copper channel, right? That means you're attenuating all your high-frequency components, and on top of that, it is extremely susceptible to noise. Your SNR is low, right? So that means you have crosstalk, power supply noise, clock, jitter. There are like hundreds of things that can really corrupt the signal. So the receiver has to be extremely good, wherein it has to equalize the received signal to correctly detect the signal, right? So that means there are so many different blocks that in the receiver itself. And the first, we have the analog front end with the CTLE and the VGA. And then you have the feed RX FFE and the digital feedback equalizer, right? So what we need is we have to understand each of these different blocks, not just in terms of how it would behave, but how it would settle down, what the parameters would settle down for our systems, our channels. Because each system is unique, each channel is unique, and the environment that the system is susceptible to is unique. You would have manufacturing variations, temperature, voltage variations. So that is the reason we would like to know and understand what are the different blocks of a receiver SerDes, and we would have to know the parameters in advance of what the SerDes parameters would settle to. And that is what we're talking about with parametric analysis. So this is the parametric analysis implementation that we are doing, wherein we are collecting data at scale in NPI, mass production, and eventually in the data centers. We are collecting the data periodically, meaning we are collecting every 180 seconds, and then we also are collecting. I will actually show you the parameters that we are actually collecting right now. Now, as you all know, with our SerDes partners, every log that we receive is in a different format, right? The logs are not easily translatable into any common standard format. In fact, even within a SerDes vendor, with 3 different ASICs, we would have 3 different logs. And this would change with every generation. So as a result, we have to deal with different kinds of formats. So what we are doing is we are parsing these log files into a standard format. We're normalizing the schema so that we're building a JSON file, which is like a meta-acceptable format, so that we can easily parse this data and look into it, so that we don't have to keep reanalyzing the log files for different ASIC, SerDes partners, different ASICs, and different generations, right? So that's where normalization comes into picture. Then, of course, data analytics. We're collecting all the data. We have to analyze it at scale. So, what are we going to do with it? Like, what is the goal of the analysis? We want to do the input-to-output correlation, meaning we want to know what is the output parameter if you change certain input parameters. If the channel changes in a certain way, how would the parameters really settle down to? If you change the temperature of a system, how does your SNR and your VGA and CTLE parameters actually change to? So this is the kind of understanding we want to know. Like I previously mentioned, it's not a black box anymore. We would like to know what exactly is happening within the SerDes system. And then, of course, once you know the system, you can categorize into different margin distributions. You can have your box plots. You can actually build anomaly detectors to understand, okay, the system is passing with good margin, this is marginal, and this is failing. So you can have all these kind of anomaly detectors to actually determine what is a good system and a bad system. And this is where the proactive analysis comes into picture, so that you can deploy your jobs into a known good system. Okay, this is a marginal system. Maybe something has to be done, or let's act like a notifier. Okay, this is a failed system. Maybe let's look into or debug into what's happening. And you will be able to debug very quickly too with all the data that you have. And of course, data utilization the goal is to implement this in the fleet and collect a lot more data as we deploy our thousands of AI clusters. So it talked about the richer telemetry, right? So what is the data that we are really collecting? This is the high-level view. We have like 63 parameters that we are collecting. Of course, forward error correction, the effect statistics with all the bins. That's one of the most important. We have your signal-to-noise ratio, prefect BER, the transmitter parameters, and then the receiver parameters, the different blocks that I showed, wherein you have the variable gain amplifier, peaking filter, CTLE, FFE. These are on the SerDes side. And of course, we need data on the system side, wherein you need to collect the rack level data, the slot port lane, temperature, voltage, link speed, firmware versions, because we've seen too many issues where firmware changes and something breaks down, right? So modulation schemes. So all the system data that you would normally think of, we would have it in a Scuba or in a CSV format, so that anybody can actually look it up without any issues and actually track the data from manufacturing to its deployment. So having said this, I would like to pass it on to Arushi, who would discuss more about how we are doing the analysis.
Thanks, Granthana. So we begin by collecting all the data across different life cycle stages, starting from NPI to mass production. It's basically to capture a wide variety of issues that we might see during ODM testing, during our lab testing, NPI, and then the noise that we can see during the production environment. So this includes all the parameters that Granthana just showed in the last slide, including I margins, jitters, SNR, VGA, error counters from thousands and thousands of links. And then we normalize the data, of course, to bring it into a format that is ready to consume and gain insights from those. Now, in the data analytics, one of our main focus was to understand how is each of the SerDes parameters that we have collected is distributed, and how can we basically distinguish between what a healthy link looks like versus an anomalous links looks like, which can show early signs of failure. And for that, in order to gain that understanding, we studied all the different error signatures we saw during the testing phases. And then we tried to understand what are the different trends that are associated with each unique error signature that we are seeing. And this is the type of analysis that we have been focusing on. And in order to understand, right, we need to understand how each feature, each SerDes parameter is correlated with each other, as well as how do they influence the link quality during the failures. We did a lot of statistical analysis. We used machine learning techniques to select the top important features that are influencing the link health. And then we tested a lot of machine learning models as well. We started with logistic regression and slowly realized the data is not always linearly correlated. We do see some complex relationship building when we see the link is going towards the failure. So we switched to the tree-based models and explored random forest and XGBoost to capture those complex parameter interactions and then failure trends as well. And then we trained the model. Once the model has been trained to capture those nuances, we evaluated the model mainly using precision and F1 score. Now, given this whole work is in development, we have been regularly revisiting the model, incorporating new error signatures, as well as re-evaluating like how is it performing while it flags an anomaly. So one of the very important things that we should always keep in mind when we look at a fleet this bigger in size is the cost associated with detecting the true positives, which are link failures, should always outweigh the cost associated with addressing the false positives as well as false negative. And yeah, so, sorry. Yes, so having talked about all the overflow of the data analytics that we are doing, this is a snapshot of the data distribution analysis across all the SerDes parameters. So on the left, we have a scatter plot of SNR versus VGA, and on the right, we have a scatter plot of SNR versus one of the receiver equalization parameter. And the blue points represent healthy, non-anomalous data, while the red points are indicating anomalies. And they have been labeled by domain experts running the tests for a certain failure signature. Now we can see here, right, many anomalies clearly fall outside the main cluster of healthy data, but a good number of them are actually overlapping with the healthy region as well. So this overlap is basically highlighting a key challenge. When anomalies do resemble the normal data, it's hard to reliably flag them using simple thresholds because it can end up in throwing a lot of false positive cases. And this is exactly why a machine learning classifier adds value, because it's able to learn all this complex multidimensional relationship between these SerDes parameters that aren't so obvious with the 2D scatter plots or different statistical plots. And that is why we understanding how different features interact and impacts the link quality becomes essential. And in order to do so, we did a couple of statistical analysis. For example, we did feature correlation analysis to check if the parameters are strongly or weakly correlated with the output. We did correlation heat maps to check what exactly is the correlation strength across the features. And then we also looked at unsupervised clustering to understand if the set of the SerDes parameters, what are the trends we can see at a lane level and a port level? Are we seeing any specific trends across different set of parameters? Now, the whole goal from talking about the data analytics and the main takeaway from discussing all this is to how important it is to have all these granular level details exposed. And we can do so many things and can gain so many insights, which are very important when we are looking at a fleet, looking at the fleet for hyperscalers, right? And we have to be proactive rather than reactive when we talk about AI clusters, because we all know the costs associated with addressing those job failures. Now, we discussed about, sorry. Okay, now in this slide, we have discussed like how we trained the model, but then how are we using that model in practice to proactively detect link anomalies? We started with understanding the failure patterns, and for each of the type of failure that we saw during the testing, we also utilized in-house testing by injecting errors and inducing more errors to bring the link down and then capturing what are the trends we are seeing. And Granthana would be talking about it in a bit. So we captured all these variations, trained our machine learning model, and then deployed it. Now, the machine learning, the model flags a data point as either anomalous or non-anomalous. And when we see there is an anomaly, we check it for a couple of runs to see if we are really confident and if it has been flagging the same link and host. If yes, we do flag the host, and that host goes under the shadow to be reviewed. Which means no AI job will be proactively scheduled on that, and that avoids the possibility of AI job interruptions due to link failure. With that, I'll hand it over to Granthana again, who will be talking about how everything that we talked so far comes together and gets integrated into a tool called Inspect, and what are the different use cases that tool addresses in the fleet.
Thank you, Arushi. Now, having said this, we are very happy to introduce a parametric analysis tool called Inspect, which is actually a statistical analysis tool to analyze SerDes channels, meaning we would be collecting the data at scale, parsing it at scale, uploading the data into easily readable SCUBA or CSV format, and then running an inference checker in real time so that we can actually get the data, whether a lane is working fine or not. So this is just one of the dashboards. In one of the dashboards, we can actually see like the different timestamps wherein a particular lane has failed. So this really helps us in double-clicking at that particular timestamp and seeing why it failed by dwelling deep into the other parameters, like we mentioned before, so that this really helps in like targeted repairs. We can reduce the blast radius by pinpointing the fault locations. We can do quicker debug, like faster root cause analysis, and as a result, the overall time to actually implement a reliable system reduces significantly. So what are the use cases of Inspect, right? The major use cases are initial screening. So we are thinking of doing like a pre-flight check, meaning before a AI job is being deployed, we would be running this particular tool so that we can actually say, yes, it's good enough to run, it's marginal, it's not good enough. So it's like a pre-flight check that we would be running to ensure that the system is good. We would be using it in repairs, in production, so that we are anyway capturing the system health periodically, and we can run these threshold checks to assess how the system is performing. Here we have few plots wherein you can actually see the distribution of the VGA, of the SNR, and even your FEC distribution slots. So here, for example, I have given two cases, lane 1 and lane 4 of the same port, and we can actually see on the real channel, there is literally not much difference between a lane 1 and lane 4 with respect to length or the topology. But how the equalization is done for each of these lanes is very different. You can see the SNR varies from 22 to 23 for a marginal case, whereas it can vary from a 27 to 28 dB for a good case, right? So, and this actually translates to the forward error correction code word bins filling up. We were actually seeing a higher FEC for this particular port because of lane 4 and not because of lane 1, and we can actually debug to the lane level. And why was SNR low? Because the VGA was not tuning to the correct value, and we were not basically the equalization was not settling to what we were thinking it was, and as a result, we were able to use inspect to actually detect an anomaly. Having said this, we would like to call to action all our SerDes partners to actually expose and help us understand the different SerDes parameters that the equalization would be settling to, just so that the system is not a black box to us, and more importantly, it will not be a black box to you also, so that we can actually collectively understand how the system is performing, right? And the second call to action that we have is for all the high-speed backplane integrators. Yuvan and Shu presented on Tuesday, wherein they are actually calling for a backplane integrator, wherein with all the system integrators, service partners, manufacturing, testing, all the backplane cable and connector vendors to come together to build a reliable backplane. So please join us with this effort. Thank you very much. Any questions?
Can you go to a microphone, please? Oh, sorry, there's.
Just a quick question. What's your telemetry sources?
The log files that we're collecting from our systems and the NPI phase.
On the switch, I assume?
Switch, ASIC.
Got it. Because I know as far as ConnectX, you're not using Doka telemetry yet, and that would be very helpful for you.
Yes, we are collecting data from basically the ASICs, like all the compute tray and the switch tray that we are connecting to, right? So different interfaces, would call for different ASICs. So there are like multiple SerDes partners that we would like to work with. Yes.
Thanks.
Sure, I have a question. So when you talk about some of the parametric data collection, you included things like signal-to-noise ratio, BER, some of the tap coefficients, I'm guessing, for the FFE. With regards to things like signal-to-noise ratio, where does that data come from? How do you parametrically capture that?
Yes, we have actually captured that. It's there in one of the previous slides. The data actually comes from the log files that we are collecting.
Okay, but how do they get into the log file? I mean, how do you know that what's being recorded in the log file is a traceable measurement?
So that's the work that we actually do, wherein we you have to work with your SerDes partner to understand how the SNR is being collected, or what your prefect BER is. You would like to, that's the work that would be, you'll have to do with the, all your ASIC vendors to understand if the SNR is being sliced, where is it being sliced, how the collection is actually being done.
So you're saying that you really rely on the IP vendors themselves to give you the confidence that the number that's being recorded is actually a reflection of of a number that's meaningful. And you can always record data, but if you're trying to record something that's effectively analog in nature, then you want to have correlation between the IP process and being able to essentially independently verify that those numbers are accurately reflecting what the analog behavior actually is, right?
Correct. So that there would be correlation with the SNR, with BER, and with your FEC bins. Say, for example, if the number is X and then if it's Y, so you know if X corresponds to a particular FEC bin versus Y would be a different FEC bin. So this is more of not what the real number is, it's more of what the margins are, what the distributions are, and if that particular value, if it's say 24 or 25, right, then we can actually, that's the work that you would be doing in NPI, whether it is 25 correct. You correlate it to your system analysis. So that's work is not part of the inspect, but that is separated. During your bring up, you will have to do that, right?
Yeah.
All right.
Okay.
Yeah.
And that's our time. Thank you.
Thank you. I can discuss offline with